I am Mia S. Mitchell, an associate professor of general internal medicine at Duke University in Durham, North Carolina, where I study weight loss interventions for underserved populations. I am proud to represent the CU Medical Alumni Association. For those of you joining us tonight who are alumni of the CU School of Medicine, the Alumni Association offers many opportunities to connect with your fellow alumni and current students. For our MD alumni, keep an eye open for an email to vote on the upcoming innovations in medical education projects. Our alumni office also has numerous ways for all alumni from the campus to get engaged. Our alumni team is always happy to help you connect with activities for your college or school. We will share more at the end of this evening's event on upcoming activities and how to reach the alumni team. Before I introduce tonight's speakers, I want to draw your attention to the Q&A and chat functions at the bottom of your screen. While we have time designated at the end of the presentation for Q&A, you're also welcome to enter a question at any time in the Q&A function. You can send your message to be visible to just the host or to all attendees. Additionally, we have alumni team members available on the chat if you need anything during the presentation. I now have the privilege of introducing tonight's speakers, Dr. Casey Green. Dr. Green is the founding chair of the Department of Biomedical Informatics and the director of the Center for Health AI at the University of Colorado School of Medicine. His research lab develops algorithms that integrate publicly available data from multiple data sets to help model and understand complex biological systems. Lucas Gillenwater. Lucas Gillenwater is a computational bioscience PhD student at the University of Colorado Anschutz Medical Campus. His research focuses on developing computational methods to deconvolute the molecular mechanisms driving co-occurring conditions in people with Down syndrome. Prior to starting a PhD program, Lucas was a high school biology teacher, a baker at Make Believe Bakery, and a research analyst at National Jewish Health. Lucas is also an adaptive ski instructor, a volunteer adaptive ski instructor with the National Sports Center for the Disabled. Please join me in welcoming Dr. Green and Lucas.
Hi, everyone. Thank you for the introduction. Today, we're going to be presenting on ChatGPT, which I'm sure you've heard about by now. And the title of our talk is ChatGPT, How AI Changes Everything and Nothing. So before we begin talking about artificial intelligence, we'd like to talk about what the ideas of artificial intelligence are based on, and that is your own intelligence. And so if we start by how we are utilizing information that we are taking in every day, we can think of the data that we consume as information that has no other annotation or extra information that would guide us to understand anything about that data. A lot of data sources that we have to be further annotated, at which point they can move from raw data that is providing us little information to what we might even label as information by annotating certain pieces of data. Moving from that to start to really understand how these individual entities interact together may be a form of knowledge. This representation of knowledge shows how we can go from data that's been labeled with information and start to understand how individual entities relate to one another. These edges are made to represent they're relating to each other in some way. Now, what's been really interesting in the days of big data is that we can start to see that entities that we thought were totally unrelated actually are related to each other. In this panel labeled Insight, we've highlighted two features that are at opposite ends of this network, but for some reason or another are related to each other. At which point we can start to see that what we thought were very distant entities, in fact, interact in some way. And a goal in our research and a lot of other artificial intelligence is to provide wisdom in the sense of understanding what is the pathway that one entity takes between itself and the other that it's related to. These pathways can be simple pathways like the one represented here, but more often than not are much more complicated. But the idea is developing artificial technology that would be able to provide us with some insights and potentially even some wisdom behind the mechanisms in our field underlying biology. And so, as I mentioned earlier, this is idea are founded in some of the things that we see about our own intelligence and our own brain as a classifier and a prediction model. And an example that I've used before is this image right here, which I'll leave up for a second. Usually this is a bit of a Q&A period where I'm able to ask people what they see when they look at this image. It looks from the outset like it's just a bunch of random black and white blobs, but for those of you who've seen it before, or for those of you with your pattern finding brains, you might start to see that it's not just black and white figures, but in fact, it's a picture that's been made black and white, but of a Dalmatian drinking from a stream. You can now maybe see that there's a head here, here's the back of the dog, and here are the legs that the dog is standing on. And so this little trick is just to show you that now your pattern finding human brain was able to identify this particular dog within the image. And I can guarantee you that if you were to be presented with this image again, that you would likely be able to identify the same dog. Just for fun, here is another image. And I would ask you the same thing. Do you see anything within this picture? And so for those of you who guessed a cow's head, you were correct. So you can see now maybe an ear here, and there's an eye, and there we have its nose going around the rest of its face to another ear and an eye. And so these images, which were likely hard for you if you'd never seen them before to identify a pattern within it, and it has now identified a pattern. You basically have trained your neural net to identify that pattern. And moving forward, you will be able to both classify and potentially even predict similar patterns within images like that. Another example is if we were to, sorry, I'm having trouble advancing my slides for a second, but there we go. Look at these word-based abilities of your brain. So again, usually if this is a participatory talk, I call in a volunteer and ask them to read what's in this red triangle here. And more often than not, people will read, "I love Paris in the springtime." But I would then ask them, how many of these are in this triangle? And the person would then look and realize that there are actually two these. So it would actually be, "I love Paris in the springtime." Your brain knows that "I love Paris in the springtime" is incorrect. You've seen other typos, you've seen other writing errors in the past, and your brain automatically will correct that. A better example might be this sentence here. "I bet that you can probably read this pretty well, even though it's all jumbled up." And again, that's because your brain has the ability to identify patterns, and knowing what you do about the way that the English language words work together, you can take something that may be a little noisy in the sense that there's a lot of errors existing in the input data, and you can process it in a way that then produces a more organized output. So again, your brain as a classifier and a prediction model is the inspiration behind the artificial intelligence models that we're exploring today. And now these artificial intelligence models have already shown up in some experimental conditions within healthcare. Deep learning, which is a term that refers to a specific type of artificial intelligence model that has multiple neural network layers, has been shown that it can do very well in tasks like identifying specific features within images from healthcare. In this particular article, it was focusing on artificial intelligence being as good as a human at spying lung cancer development. And this was using a particular type of artificial intelligence that we label as convolutional neural network. And so what this technology did is it did just as well as a human at identifying the particular features within these radiological images that were indicative of lung cancer developing. Another example comes from Google's DeepMind, which is a section of Google, team in Google studying artificial intelligence. And they were able to utilize very large databases of protein structural data. And they developed a tool called AlphaFold, which was able to predict the shape of nearly every protein known to science, and also predict those that we currently don't know, but based on our understanding of the other proteins that we've seen so far, are possible proteins that we may identify in the future. And these hairballs that you see here, this is coming from a New York Times article, are showing structural representations of proteins in all of biology. I'm not sure if these are specifically human or they might be bacterial or other organismal proteins. Nevertheless, this is one of the many examples that exist now of artificial intelligence being applied in the field of science, in this case for the purpose of protein prediction. So now I'm going to turn it over to Dr. Green for the next slides, because he's going to focus on the actual science behind ChatGPT. And so Dr. Green.
Yeah, so it's really exciting to be here and to get to share some of the amazing advances happening in artificial intelligence. It's interesting because being in the field, we've seen this steady progression of advances through imaging, through protein folding, and then all of a sudden my phone started ringing off the hook about a year ago when ChatGPT released when OpenAI released their product ChatGPT. And one of the amazing things about ChatGPT is that it is a remarkably good writer. So what we know when we apply these algorithms is that we need training examples. We need to be able to tell a computer how to do what we want without giving it explicit rules, but instead giving it data. So Lucas, can you kick off this animation? So if you want to train a computer to write, you can ask it to essentially fill in the blank. And this is how these models are trained. So what folks who are training these models do is they take an enormous amount of text written by humans, generally whatever they can get access to on the internet. And then they provide it to a computer program up to a point, and then they chop it off and they train a computer to give them sort of whatever comes next. And if you do this, you end up with computer programs or machine learning models, these large language models, as they're called, that can generate text that sounds like it was written by humans because it's trained essentially on an enormous amount of text written by humans. And then the challenge is, okay, so now I can generate text that is plausible. How do I generate text that is useful? So the second thing that they do is after they've trained a model to generate text that is, sounds good, sounds like it could have been written by humans, they do something called reinforcement learning with human feedback, which is a really complicated way to say they provide potential answers to people, and they have those people effectively say, this looks good, this doesn't look good. And then they feed that back into the algorithm to try to generate more and more answers that look good and fewer answers that don't look good. And there's many different ways that they do this. Sometimes they'll ask people to edit the text that was produced to make it better. There's a lot of different strategies that are used, but at the end of the day, it all comes down to the first part, which is training a computer to generate to be able to generate text that sounds like it was generated by a human. And the second part, which is trying to train that computer to then generate text that is desired by humans. So I work in the field of biomedical informatics. I chair our department of biomedical informatics. And one of the things that I like to always think about is like, what business are you in? In biomedical informatics, the business that we're in is the serendipity business. So we want to put the right information in front of the right person at the right time to make the right decision. And often with these large language models, what we're trying to do is give people the capability to take potentially large amounts of text and extract exactly the right information, or to be able to sort of surface the right information as the next step in a process. I have an example of one of the ways that we do this. So this is actually not AI powered. So this is just putting the right data in front of the right person at the right time. We know that pharmacogenomics can provide benefits to individuals who are considered for medications where the impact of those medications can be influenced by their genetics. But no one actually does, I would say pharmacogenomic testing is very rare in practice. And the reason it's very rare is because if you wanted to do a pharmacogenomic test, someone's in your office, you order the test for them, that test, that sample then gets sent out, you get back a 90-odd page PDF, you look at that PDF and you say, okay, these are the genotypes that they have. You then take those genotypes to a table like the one on the left, and you say, okay, is the drug that I was about to prescribe in this table? That takes a lot of time. It's not generally reimbursed. And so in general, we prescribe the medications that work for most people, not necessarily the medication that will work best for someone that we're considering treating. What we do in terms of the idea of serendipity on the right here, this is something that happens at UC Health for folks who are part of a biobank study where we've been able to return structured information about their genetics. If in that case, a provider was going to order, in this case, Plavix, for someone who we think wouldn't benefit from Plavix in the same way, instead we recommend, so as soon as they put that in, this screen would pop up and say, we recommend you remove this and apply one of the following. And so this actually works. So this is what I mean by serendipity, surfacing exactly the right information at exactly the right time to have someone change a decision. And I think AI is sort of fundamentally changing the landscape of what we can think about in terms of serendipity. So this is an example that I thought was probably one of the most interesting papers of this year. So in this paper, the authors took basically physician responses on the Reddit Ask Docs, and they created chatbot responses to the same questions. And then they asked individuals to rate whether those responses were empathetic or very empathetic, or somewhat empathetic and not empathetic. And it was really interesting that the proportion of responses rated empathetic or very empathetic was about 45% for the chatbot and 4.6% for the physicians. So this led to a bunch of articles that essentially said, AI or computers are more empathetic than doctors. Clearly, this is not true, right? Like, these are physicians who are, after hours. The way this forum works, they're licensed physicians after hours who've decided, hey, I'm going to go answer patient questions on Reddit. Like, you can imagine those of you who deal with a bunch of messages in your inbox at the end of the day. Like, there's no way those people are not empathetic, but somehow the AI system is able to convey that empathy really effectively. And I think this magic goes, this kind of goes back to how these methods and models are trained. They're trained to generate text that people like. And we like text that's empathetic, right? And so we've really created a system that can help us potentially convey empathy that we feel, but may not be great at conveying at the end of the day when we're asking questions on Reddit. And so I think there's lots of different ways, both from the serendipity side and from kind of how we interact with patients and others, that these methods can be helpful to us if they're deployed carefully and if we understand many of their limitations, especially in terms of biases and their ability to create a reality that doesn't precisely match our own. So what are the challenges with these models? I'll let Lucas kind of jump in after this and really dive into some of these in detail. But I think there's many challenges, but I think they all go back to a few key principles. So one is the types of models that we're using, like ChatGPT and other large language models. These generative models, they're created to be plausible, but they're not necessarily accurate. So they're very good at generating stuff that sounds good, but it's not necessarily true. And so when people are thinking about how to use these, I often advise them, if you are using a model to support you as an expert in an area where you have expertise, that is a good use of these models. If you are using these models to give you expertise in an area you are not familiar with and would not be prepared to answer questions in, that is a dangerous world, because they can generate stuff that sounds really, really good. Unfortunately, it may not be true. Another issue that they can have is they can memorize their training data. So one way to fill in the blank really well is if you've seen the same sentence 15 times because it's really common, it's a quote or something, it becomes really easy to just spit back that quote. If you are using these in healthcare, the way these models are often trained, and many companies that provide these models deploy them, things that are input into those interfaces are often used to train the models and continue to fine tune them. That's part of this reinforcement learning with human feedback part. So if you, for example, were to put some regulated data in, protected health information or data about students that could be covered by FERPA, that can end up back in the model, which means that other people can then receive it if the model memorizes it. And so it's really important to understand how any data that you put in these models is used by the companies. I don't love reading terms and conditions any more than you do probably, but for anytime I'm going to use one of these models, I am deep in the terms and conditions because I want to know how they're going to use what I input to it. And then the final part is, and Lucas will talk more, much more about this. That RLHF step, the reinforcement learning with human feedback, is just so important in terms of defining the space in which the model will be able to provide accurate answers as opposed to just plausible answers. And we get almost, usually when you're using the systems, you have essentially no information about how they're trained and what space they're trained in. So these are some key challenges, and I'll hand it back over to you, Lucas, to wrap up.
Thank you, Dr. Green. So what you were alluding to there at the end is the ability of people to misinterpret models, or models to misinterpret the information that's coming in. And so I thought that this was an interesting adaptation of the framework that I presented earlier of going from data to wisdom. But people can then take their own outline to these features and identify, in this case, a conspiracy theory, or there are ways that we can gain misinformation from these data. An example that Dr. Green was talking about is that they may only be as good at identifying things that were within the training data that went into the model to begin with. And if you were to take something outside that training data, they might have trouble. For example, if you had a model that was entirely trained on dog images, then determining if an image is a Chihuahua or a muffin may be a very difficult problem for that image classifier. And it turns out that that has been true, that these models have had trouble with these two, blueberry muffin or Chihuahua, which from looking at these images briefly, I think that we could all understand. But I'm fairly confident that if any of you were to spend some time on it, that you would in fact be able to pick which one's a muffin and which one's a dog. And to add to that, another way that we can confuse some of these models is, again, knowing how they were trained, we can trick them. And so this is an example of a model that was trained as a classifier. And if you were to give it this image, it's able to say with very high confidence that this is a banana. However, if you take the same image and you add this sticker to it, which this sticker, you just stick it in the middle of the image, this then confuses the classifier. It no longer has very high confidence that it's banana, but instead it thinks that it's a toaster, probably relying on specific parts of the sticker for that classification. Maybe it's kind of reflective or metallic. And so in both of these cases, the models and their training material are going to be one way that you can affect the model. If it's been trained only on a specific data set, it may have trouble with things outside of that data set. And also in the way that the model is trained, you can sometimes easily confuse these models by giving it a new image that it hasn't seen before. And another example that's also been in the news of artificial intelligence being used, and this is a bit more nefarious than these other examples. Instead of just trying to trick the artificial intelligence, people were using artificial intelligence to trick other humans. And so in this example, this was another article that I read in the New York Times that went over the fact that a lot of people have been producing new travel guides. If you look at the dates for all of these travel guides that I have displayed on the slide, you can see that they're all 2023. And if you go to Amazon and look specifically at some of these, they look pretty legitimate. This one right here has a France travel guide. It's written by Mike Steves. It has a 4.4 rating over 37 ratings. It seems to be not that expensive. It has a legitimate description of what this book is, and I could see easily looking at this and thinking, oh, this would be great for my trip to France. But maybe we should look more into Mike Steves. So here is Mike Steves' image blown up. And when you look at this, maybe you can immediately see that it's kind of weird. It looks like he has a second earlobe underneath of his left ear. It looks like he's wearing a shirt that has stripes on one side and is just plain on the other. The background just seems to be kind of weird. And in general, Mike Steves is a name that's pretty close to a PBS travel guide creator, Rick Steves. And so maybe this isn't a real person. Secondly, if you start to look at some of the reviews, you can also see within these reviews that maybe these were created by artificial intelligence as well. So here's one verified purchase 5-star review. My greatest desire is to know France. This guide has been spectacular, being able to choose the season, to know what climate we like best, knowing that their language is English. It teaches you the tourist sites, and its history is incredible, which does not seem to make a lot of sense, being that France's language is not English. And if you were to look at some of the other actual purchases, people showing some of the images from this book, you can see that it's as though you would think that someone just copied and pasted things from the internet, put it in there, but that's in a way what these models are doing, is that these models have been trained on large swaths of data from the internet, and people were using it to create an output that would look as much as possible like a travel guide without being a travel guide. And so I bring this up and these other adversarial examples just to reinforce the point that these chatbots really require a lot of validation, and that it's likely that the abilities that we currently are seeing within these chatbots that we might ascribe to reason, so this impressive reasoning abilities of these large language models, are often very dependent upon the prompter knowing the answer. And so that reinforcement learning human factors, that human is in fact an expert, which was able to reinforce the model in a way that it would be able to provide you with more accurate and truthful answers. And that's something with the models that, especially these publicly available ones, that you should be skeptical of. And that we will need to continue to develop them in a way and evaluate them in a way to make sure that we're not just being fooled by their abilities to make something that looks a lot like a good answer, but is actually a good answer. And so with the last couple of minutes, I'm just going to jump back to an example of how I'm using these models in biological research. And for this one, I'm just going to share some of my research. I mainly study individuals with Down syndrome. And so on the left side of the slide, we have Lucas Warren, who was in 2018 the first Gerber baby with Down syndrome. And Lucas, much like all others with Down syndrome, has trisomy 21, which is a way to say that Lucas has 3 copies of chromosome 21 as opposed to the usual 2 copies that we all have. Down syndrome is the most prevalent, what we call aneuploidy, which is, again, a condition in which you have multiple copies of one chromosome in humans. So there are about 1 in 700 births of people have Down syndrome. And it's a population that's growing in the United States, and the people who have Down syndrome are now living much longer than they used to, thanks to improved care, I think, and more general acceptance. And with these people with Down syndrome living longer, we're also seeing that people with Down syndrome have several other co-occurring conditions. And so if someone has Down syndrome, they're almost 100% likely to develop Alzheimer's by a certain age. And what we do see as well is that those who develop Alzheimer's, they develop it at an earlier age than we would see in those who have 2 copies of chromosome 21. Furthermore, people with Down syndrome are much likely to have autism or be epileptic. They're much, much more likely, up to 400 times more likely than people with a typical chromosome set to have pediatric hematological disorders. So these include various types of leukemias. And so we see a lot more development of leukemias in children with Down syndrome. There's also a much higher risk of developing autoimmune disorders like alopecia, arthritis, celiac disease in people with Down syndrome. And these people also have higher rates of obstructive sleep apnea and pulmonary hypertension. However, at the same time, while we see that people with Down syndrome have these increased rates of various conditions compared to those with typical chromosomes, we see a decrease in rates of other conditions. So people with Down syndrome are less likely to have coronary artery disease or high blood pressure, and also much less likely to develop solid malignancy, so much less likely to develop solid tumors. So we see these age-related disorders that are much more common in people with Down syndrome, while at the same time, an age-related disorder like cancer is less common. And so we as a research community are curious as to see if we can understand what's the underlying biology that leads to this set of increased conditions and decreased conditions. And so to do so, we have been looking at some of the underlying molecular features. And so I know that this is an alumni crowd here, but for those who may have not been in a biology course in a while, I just wanted to give a review of some of the molecules that we're looking at to better understand these underlying biologies. So the central dogma of molecular biology is that information flows from DNA to through transcription is transcribed into RNA. And then these RNA pieces are then translated into proteins. And then these proteins are going to interact with different small molecules in our bodies known as metabolites. So metabolites can be things that your body produces, and then also things that you take into your body through eating or exposure to the environment. And so within these different features, we have genomics that relate to DNA, transcriptomics relate to RNA, proteomics relate to the proteins and metabolomics. And these are answering different questions if we look at these features alone. The DNA can tell us what the blueprint is and what can happen in humans, but then we look at RNA to see what appears to be happening, because different genes will be turned on with different other regulatory signals. So if a gene is expressed, that is something that could lead to then a protein from that piece of mRNA. mRNAs can also act on themselves, and they have other regulatory features, but for the central dogma of biology, these RNAs can then be translated into proteins. And these proteins will act both as enzymes and structural components of the cell. But then these proteins can also interact with metabolites, causing metabolites to change from one type to another. And all of this is providing further signaling these molecules interact with each other in various cells within our body, and they ultimately manifest in what we call a phenotype. So that would be the trait or the representation of those interactions in some condition, some disease, or some different symptom within that disease. And so an example of how we can use these molecules to better understand how people with Down syndrome develop Alzheimer's disease, an example of this is that in someone with 3 copies of chromosome 21 or trisomy 21, they have an increased expression of a particular gene known as APP, which stands for amyloid precursor protein. So this amyloid precursor protein is an intermembrane protein that when it is increased, it leads to an increase in A beta or amyloid plaque, or A beta, which then leads to an increase in these amyloid plaques. And these amyloid plaques in combination with neurofibrillary tangles lead to Alzheimer's disease as we know it now. And so that's a pretty clear mechanism that those with Down syndrome would have an increased representation of that gene, which would then lead to more plaques, which would then lead to Alzheimer's disease. But for a lot of these other conditions, it's not quite as clear. And so we're able to look at a lot of these molecules in large data sets now and utilize deep learning and other machine learning techniques because it's so much easier to get this data. This is showing a graph of a cost per human genome from the year 2001 to 2021, with the line on top being Moore's law, which is based in computer chip development, but assumes that we're going to be able to double and reduce the price at such a quick rate. And what the line is showing is that the price of a human genome is becoming cheaper at a rate faster than what is predicted by Moore's law. And so we're able to create these data sets of genomes, but in addition, we can also look at other types of data. And the Linda Cernick Institute at this campus, at the Anschutz campus, has developed the Human Trisome Project. And this is a panomics, which means it's looking at genomics, proteomics, metabolomics, transcriptomics. And it's also studying the natural history of individuals with Down syndrome and using deep clinical metadata, creating this biobank that researchers can then use to better understand how these molecules interact and lead to these diseases. If you're interested in understanding this further, I'd recommend that you go visit trisome.org, and we'll take you to this landing page. And you could even utilize this tool known as Trisome Explorer. If you were to be interested in a particular type of chemical, you can see how those chemicals differ in the samples of people with and without Down syndrome. So they're now, because of the reduced cost, we've been able to generate thousands of these data sets, and we're starting to look at how these molecules interact with each other to understand what's the underlying biology within people with Down syndrome of these diseases. The problem is, again, the central dogma that I presented to you earlier is a bit simplistic, that these molecules interact in very, very complex ways. So you can have a gene transcribed into mRNA, but this RNA can also provide further regulation to itself. The mRNA can be translated into a protein that then regulates the production of mRNA. This protein can have enzymatic activity that's going to cause a metabolite to change into a different product, but then different ligands can signal proteins to either increase or decrease their enzymatic activity. And then all of these things may be affected by various environmental factors, from a particular drug that someone is on, or even other things within our, what we might call exposome, our exposures that we have within the environment. And so we're utilizing deep learning to better understand these features. Just providing even further context to this, one thing that we have been able to reveal within people with Down syndrome is that they have increased signaling molecules known as interferons. And in this figure on the right is a representation of people with trisomy 21 versus the left, which is euploid, meaning a typical number of 2 chromosomes 21. They have increased interferons and interferon receptors, which in the case of SARS-CoV-2 infection, we were able to observe, or I guess, yeah, coronavirus infection, we were able to observe that in people with Down syndrome, due to this increased rate of interferon signaling, they had increased likelihood of developing the cytokine storm, which may lead to cytokine-driven pathology. But we've also been able to observe that within people with Down syndrome, that there are some drugs that might block that signaling. So this image on the right is now zooming into one of the interferon receptors around the circles on the left, and it's showing an interferon receptor that would signal a molecule to create the cytokine-inducible genes. We can block this production using a drug known as tofacitinib, which focuses on this particular protein called STAT1. And trials have been going on here on campus to understand how that would work in people with Down syndrome, because oftentimes in the past, people with Down syndrome have not been included in this research. And so here's an example of tofacitinib that was used to treat alopecia areata, a type of autoimmune disease in people with Down syndrome. And the left is 1 month, the right is 3 months. And I think that you can pretty clearly see that this person has grown back a lot of the hair that they have lost from this autoimmune disorder. And so tofacitinib was able to block that and shown great success in people with Down syndrome. However, we may still be concerned about how that drug could interact with other drugs that people with Down syndrome are taking, because as I presented earlier, they have a lot of other co-occurring conditions. So in that case, I've been exploring how we can utilize this molecular pathway information to understand the biological mechanisms. If I were to utilize something similar to or another knowledge representation other than within large language models and look at how alopecia interacts with tofacitinib, I was able to see that phenytoin came up as an intermediate node in this graph. And plugging this into a large language model, I was able to see that in particular, phenytoin is an anticonvulsant that is used to treat epilepsy and other seizure disorders, and that it may moderate the drug-drug interaction between tofacitinib and phenytoin through a particular enzyme, cytokine P450. And so this is something to be further evaluated. It seems that it's something we can understand at this point, but it's something that I was able to utilize large language models to better explain mechanisms that we were observing in the drug to begin with. Now, there's a lot of other research to be done here and potentially other drugs related to those other conditions that I'm interested in. This is just one example. And so with that, I believe that's the end of our presentation. And I know that Dr. Green and I will be happy to take any particular questions.
So thank you all for that. I'm going to start with a question, and I'm going to start backwards because I'm going to ask Lucas a good question. Just when you were talking about COVID and how it interacts with patients with trisomy 21 versus euploidy, you mentioned cytokine-driven pathology, and can you explain what that is?
I can explain it as much as I can as a non-clinician and as someone in computational biology. Yeah, would appreciate any elaboration. But my understanding is cytokines are these inflammation signaling molecules that we have within our body that are usually released in the case of some infection. Like if you were to be infected by a virus, for example, then it will trigger your immune system to create T cells and B cells, and those cells are signaling to each other using these signaling cytokines. It's good that when it happens then, because then it can go in and kill that virus that has invaded your body. When it can be bad is that if you have so much increase in the cytokine signaling, that the cytokine signaling leads to too much inflammation, and even autoimmune disorders where it's talking, or where your immune system is attacking your own cells. And so what we were observing in some people who had COVID infections is that they had too much cytokine signaling that basically overloaded their inflammatory system, and cells began attacking organs that they shouldn't have been. And that led to some organ failure. And so for that reason, and people with Down syndrome have higher rates of interferon signaling, cytokine signaling. So it's potentially an avenue for treatment.
Okay, and then someone has put in the chat that cytokines are chemical messengers that coordinate and regulate immune responses, not always inflammation, but play an important role in all immune responses. An immunologist. Okay, thank you. Amy Bernard, PhD. I have another question, and wait, there's more in the chat, though, so let's see who's got him.
Yep, maybe I think this question is really interesting on the Amazon bit. I was about to ask you the same question, even though I realized we're co-panelists. So if I understand correctly, Lucas, there are people who will entirely synthetically generate books, automatically buy those books, and then generate synthetic reviews of those books from authors that are entirely AI generated. Is that correct?
That's correct. So it's this loop we see of artificial intelligence develop books and then using artificial intelligence also to create the reviews of the book.
And so someone else is asking a question about how safe is ChatGPT and what might be the risks of that? And I would ask something that is related to that. That I was at a presentation where someone used ChatGPT to show us, like, sort of said, please come up with a 500 words written by X, and X was that particular person, and give me also 5 references. And so it came up with something, some of which was plausible, but actually created references that did not exist. And so I find that terrifying. And so I was wondering if you could speak to that.
Yeah, so there's a recent example that's been in the news too, where a lawyer was using it to write legal briefs and it made up cases. Yeah, so this goes back to the challenge that these things generate stuff that's plausible, right? So it knows that scientific text should be referenced, or it has learned that text that looks like this often has this other thing after it, which happens to be how we denote references. The same is true of legal text. But because these systems, the modern generation of systems, are not grounded in sort of essentially principles of sort of truth, or what we might view as reality, it means that, it will sound great, but it might be wrong. So this is why I think using these systems when you're an expert in an area can really empower you. On the other hand, using these systems when you are not an expert in an area and don't know, for example, that case isn't a real case, can like undercut you. And so I think you have to be really careful on that. The other thing that I would highlight as an issue is that the way these models are trained, they're trained on essentially, a massive amount of human text written by humans, which contains all of the biases that, we as society have. And so I often will talk about this issue of bias laundering, where people will say like, oh, this was generated by a computer, it can't be biased. And it's like, no, the training data is entirely and inherently biased. And these system developers are trying to build guardrails around this, but they're post hoc guardrails, right? So the underlying data and the underlying models are biased. And then what they do, for example, there's a tool called DALL-E, which will generate an image from text. So what OpenAI does when they provide you access to DALL-E is they will try to identify if you're trying to create a person or a collection of people. And if they can identify that you're trying to create a picture of a person or a collection of people, they will add a diverse before that. And that's basically a post hoc fix to try to create, any group that they create would be diverse. If they don't do that, if you use the raw underlying models, and you ask it to create a doctor, that doctor will almost always be a white male. And so, there are lots of people thinking about how to try to fix these models, but it's worth recognizing that they are fundamentally and inherently biased. And while there are people trying to fix it, those are post hoc corrections. And so, I think you have to be very cautious with their use.
Thank you. We're getting more questions in the chat. I just want to do a quick follow-up and ask, can these models be trained to say, I don't know, or unable to answer the question?
Do you want to handle that, Lucas, or do you want me to?
I think you're probably better. I see that sometimes it says, I'm not a medical expert, but then it still gives you an answer.
Yeah, so often the way that many folks who produce these products are dealing with it is they're trying to predict that they're trying to build a classifier that says the model will not actually be able to provide a good answer to that question. And then when they do that, they then kind of stop the response. So their ability to say they don't know is about as good as their, people's ability to build a model that predicts what they won't be good at. There are enough times that I use it where I'm like, okay, they've built nice guardrails. And then every once in a while, it'll generate something. And I'm just like, oh, okay, we missed that one. So I think the answer is there are ways to have them say, I don't know. But again, it's all kind of post hoc fixes after the fact. So it's kind of the same issue. They're powerful tools, but I agree with, this is an important risk.
And I think this question from me, okay, how was ChatGPT related to the Down syndrome? Was it helping you with your research because it's so complex?
Yeah, I think I really buried the lead on that. It's exactly due to this overwhelming complexity that we see occurring based on the upregulation of the around 225 genes located on chromosome 21. So it causes a great deal of regulatory changes. And so I've used models similar to large language models like ChatGPT to just try to better predict that regulatory nature of those interacting molecules that I presented. And then I think there's also potential for then being able to create human readable text based on some of the mechanisms that we're predicting. Of course, with the caveat of any sort of mechanism that I am able to predict, I'm going to have some biologist with very good understanding evaluate whether or not that's truly a legitimate hypothesis to explore, or again, if it's totally not plausible. But yeah, it was mainly just out of the fact that these data sets with a lot of different molecules that we're able to measure now are requiring these technologies that have increased inference power, similar to something like ChatGPT.
So as a PCP, I'm interested in this question. How soon will AI take over the PCP role?
Yeah, so I think what I would say is, I think there's a lot of opportunity for these AI systems to help PCPs do their job more effectively, but I don't think we're talking about taking over the role. I think we're talking about, in my ideal world, kind of what I imagine is that these systems can help PCPs or others kind of spend more time being able to focus on their patients. So automate away some of the elements that can be taxing or time consuming, like making notes that follow a specific format, and allow PCPs to do what they're going to do better than anyone else, which is interact with their patients, listen to them, empathize with them, and then make decisions based on both what they're hearing and potentially, what might get surfaced. You could imagine an AI model running on a chat transcript that might be able to surface something to someone like, oh, this and this might be worth thinking about together. But I don't think it's, we're not, at least to my knowledge, we're not talking about replacing PCPs. What we're talking about is sort of empowering PCPs.
Okay, thank you. I think that makes it feel a little bit better. So another question is, will these AI models start to become specialized to topics or areas, or are they already specialized to topics or areas?
I can take that one.
Sure.
I've worked with some models that are already specialized. Oftentimes it's based on the models being trained on a different set of training materials. And so there are several models that, for example, are only biomedical natural or biomedical large language models. So they've only been trained on sources like PubMed, for example. And I believe that there's also some people work on a process of fine tuning a model where you have a model that's been trained on a very large general data set. And then after that general training, you then apply fine tuning, which is more specific to the features that you're looking at. So again, maybe if you're only looking at one particular research area.
Okay. And this might be somewhat related, but this definitely goes back to something earlier we were discussing is when you're training on an AI system to be accurate instead of just plausible, when do you know you've trained it enough to be accurate and not just plausible?
So I have two different answers here. So one is in the context of large language models. I think the techniques that we are using are fundamentally not designed to create output that is accurate. They're designed to create output that is plausible, that humans like. So I think there's kind of a fundamental limitation here. There was a previous set of AI chat systems from the 80s that was, and I learned recently from my 5-year-old daughter that the 90s are the olden days. So pre-olden days, I'll say. In the 80s, there was this idea of sort of semantic reasoning and building semantic reasoning into building AI systems based on reasoning, right, around facts and premises and axioms. Those have been entirely discarded at this point in favor of these machine learning models. But I really think we are going to need to start to bring some of those principles back in if we want to get something that is sort of going to be able to be more effective at getting to truth. So I think for that class of models, I think there's going to be some fundamental methodological work. In terms of other
Wait, can I
predictive
ask you a
models,
question about that though? What
Yeah.
about the bias? How does that come into play based on what you just mentioned? Semantic models.
Yeah, so those will also be biased because they're going to be based on human understanding, and much of which is developed in the context of, for example, research that doesn't equally include women, and so they do have similar bias issues, but to me, there's like the glimmer of being able to potentially build systems that are able to get at whether something might be true. And I think the sort of large language models are a bit far away from that as far as I've seen. There's an entirely different class of kind of predictive models where we're trying to just build a predictor that's not trying to say generate new text. I think those type of models, there's a lot of different strategies that we use, cross-validation, nested cross-validation, independent held out test sets that we use to kind of assess if we're there. But neither Lucas nor I spent a huge amount of time on those in this.
All right, and then I think our final question will be from someone who's talking about pharmacogenetics and could AI be more helpful or harmful? This person, I guess, had some testing done for some medications that were supposed to help down what they could potentially use. And do you think that it could become streamlined and cheaper in the future?
So our pharmacogenomic strategy through the Center for Personalized Medicine is not based in AI at this time around kind of, dealing with these reports and summarizing information. I could imagine a scenario where someone uses a large language model to kind of extract key features out of a report and surface them and convert them into structured text. So I guess I'd say I could imagine that. Our strategy is to try to keep it as sort of small structured elements that we sort of have built clinical decision support around already. So that we don't need the AI, but for places that don't have that built in, I guess I could see a path there, but we have not explored that path. There's other ways that we're using kind of AI in the health system.
Absolutely. Well, we are right at, I'm in the East Coast at 8 o'clock, so I think it's 6 o'clock your time. So I want to thank you again for a wonderful presentation. And you can see by the questions, we had some very engaged people in this presentation. So thank you so much. And on behalf of our attendees tonight and the CU alumni, Anschutz alumni, I want to thank Dr. Green and Lucas for sharing their time and expertise with us. So thank you so much. And before we close this evening, I want to share a couple of upcoming events for our alumni community. All alumni can join us for CU Night at the Rodeo at the National Western Stock Show on January 19th. Additionally, CU Dental is hosting their annual alumni reception at the Rocky Mountain Dental Convention on January 19th. We will share information on both these events in the post-event email. Thank you again for joining us, and we appreciate you for tuning in and for all that you do as healthcare professionals for your campus and your community. Have a good evening, and we hope to see you soon. Thank you.